So we're looking at the sum as k goes from 1 to infinity of 1 over k squared plus 3. So the question I want to ask is, can you determine whether this series converges using the direct comparison test? So does the direct comparison test work with this problem? And the answer to that is yes. Remember, for the direct comparison test, what do we need? We need to be smaller than something that is convergent. And the way we would prove that is we would say k squared plus 3 is greater than k squared. So 1 over k squared plus 3 is less than 1 over k squared, and everything here is positive, so that's good. We know the sum of 1 over k squared converges based on the p-series test. Typically, when we use these comparison tests, we like to converge to a p-series. If p is 2, it converges. So we are smaller than a convergence, so our conclusion is the sum as k goes from 1 to infinity of 1 over k squared plus 3 converges by the direct comparison test. So let's take a look at another example. What about this one? The sum as k goes from 1 to 5 of 1 over k squared minus 5. Excuse me, 1 to infinity is what I want to say. If it's 1 to 5, it's going to converge. If it's 1 to infinity, then it requires us to think about it a little bit. What is the sum as k goes from 1 to infinity of 1 over k squared minus 5? So my question again is going to be, does the direct comparison test work here? Can you successfully use the direct comparison test? Well, let's think about it. K squared minus 5 is less than k squared. So 1 over k squared minus 5 is greater than 1 over k squared. Okay, but the sum of 1 over k squared converges. If I'm greater than a convergent, that tells me nothing. So my series, the sum of 1 over k squared minus 5, in essence, is greater than the sum of 1 over k squared. If I'm greater than something that converges, I don't know, so the test is inconclusive. And that's our issue, right? I mean, the direct comparison test only works for a relatively small number of series. But we want to go ahead and do this. And we're going to answer our question using something called the limit comparison test. So taking a look at this, we've got the sum as k goes from 1 to infinity of 1 over k squared minus 5. And what are we going to say here? I have to compare this to a different series. So the elements of our sequence, a sub k, is 1 over k squared minus 5. B sub k is what it is going to behave like. So let me ask you this question. What sequence do you think a sub k most behaves like? A sequence that we know something about. What will that be? And the answer to that question is 1 over k squared. Now, how does this work? What are we going to say for our discussion here? Typically, we want this to work for these sequences to be positive. So a sub k is positive eventually once I get beyond 3 or greater than or equal to 3. So as long as it's positive eventually, b sub k is positive forever for all k. So a sub k and b sub k are positive. So that's one of the things that we need. Then we're going to look at the limit as k goes to infinity of a sub k over b sub k. So rather than playing with the direct comparison test, we're going to try to take a look at what that limit will be. So what are we going to get there? We're going to take a look at the limit as k goes to infinity. A sub k, 1 over k squared minus 5 over 1 over k squared, which requires a little bit of algebra for us to do. So we'll take the limit as k goes to infinity of 1 over k squared minus 5 divided by 1 over k squared, which is the limit as k goes to infinity of 1 over k squared minus 5 times k squared over 1, which is the limit as k squared goes to infinity of k squared over k squared minus 5. Now, how do we do this? Back in Calculus 1, our strategy was to divide top and bottom by k squared. In Calculus 2, we could change them to x's and use L'Hopital's rule if we want. Let me go ahead and do that Calculus 1 strategy first. So if I've got the limit as k goes to infinity, limit as k goes to infinity is what that should have said, of k squared over k squared minus 5. We're going to divide top and bottom by k squared. Divide the top by k squared. Divide the bottom by k squared. So we have the limit as k goes to infinity of k squared over k squared over k squared over k squared minus 5 over k squared, which is the limit as k goes to infinity of 1 over 1 minus 5 over k squared, which is what? The top goes to 1 as the bottom goes to 1 minus 5 over a large number, 1 over 1 minus 0, which equals 1. Now that's good news, because 1 is a positive finite number. So here's our goal. If the limit as k goes to infinity of a sub k over b sub k is a positive finite number, so what does that mean? Make sure we're clear on our notation. It means it's bigger than 0, so 0 is less than the limit, which is less than infinity. If that occurs, then the limit comparison test applies. So what are we going to say here? We're going to say both series will be of the same type. Now, what did we have before? We had a sub k was 1 over k squared minus 5. B sub k was 1 over k squared. What do we know? We know the sum of 1 over k squared converges. Why? Because of the p-series test. So my conclusion will be what? The sum of 1 over k squared minus 5 will converge by the limit comparison test. So again, here's our idea, right? If the limit as k goes to infinity of a sub k over b sub k is a positive finite number, in other words, that limit is more than 0 but less than infinity, some kind of a real number more than 0, then the limit comparison test applies, which means both series are of the same type. So we're always going to try to compare something typically to a p-series. So let's go ahead and try another one. What if I have the following? I'm interested in the sum of 2k plus 7 over k squared plus 8k plus 3. And our goal is to proceed using the limit comparison test. That's going to be our goal here. Use limit comparison test. So our a sub k is going to be 2k plus 7 over k squared plus 8k plus 3. What will b sub k be? What do we want to compare this to? What will be the best sequence to compare it to determine whether our given series converges? So what do you think about that? What would our best sequence be to compare this to? And I would say that the answer is, what is this behaving like? It's behaving like 1 over k. Now, how did I know that? I just look at the highest powers. 2k on top, k squared on the bottom, k over k squared, 1 over k. You could have said 2 over k, but 1 over k is a better answer because we know 1 over k, the harmonic series, diverges. 2 over k is a multiple of the harmonic series. So when possible, we want to go ahead and compare our given series to p series. And 1 over k is a sort of a p series. All right. So what are we going to do? How does this process work? Let me look at the limit as k goes to infinity. A sub k over b sub k. We have the positive requirement. These things are positive always. So that's not a concern. And then my goal is to get a positive finite number. I want the limit to be more than 0, but I want it to be less than infinity. So what will that be? The limit as k goes to infinity of a sub k, 2k plus 7 over k squared plus 8k plus 3 divided by 1 over k. We take the ratio of these two sequences. And what does this equal? This equals the limit as k goes to infinity of what? Of 2k plus 7 over k squared plus 8k plus 3 times k over 1, which is the limit as k goes to infinity of what? Of 2k squared plus 7k over k squared plus 8k plus 3. And then the question I'm going to ask you is, what is that limit? What will that limit be? So answer that question for me. On the previous page, we used Calc 1 strategies. On this one, let me go ahead and use a Calc 2 strategy. We recognize that it's infinity over infinity, so I can use L'Hopital. When I use L'Hopital, I like to change it to x's because x implies real numbers, k implies integers. So limit is x goes to infinity of 2x squared plus 7x over x squared plus 8x plus 3. Right now it's infinity over infinity, so when that happens, I can use L'Hopital. So take the derivative of the top, take the derivative of the bottom. What will that give me? We'll have the limit as x goes to infinity. What's the derivative of the top? 4x plus 7. What's the derivative of the bottom? 2x plus 8. And it's still infinity over infinity, so I can use L'Hopital again. What will that give me? Limit as x goes to infinity. Derivative of the top is 4. Derivative of the bottom is 2. But that makes me very happy because 2 is a positive finite number. So 0 is less than 2 is less than infinity. So based on the limit comparison test, we say both series same type. LCT, both same type. So we have to go back and ask ourselves, what were our two sequences that we defined? we defined this one. And we define this one. What do we know? We know the sum of b sub k, the sum of 1 over k diverges because it's the harmonic series. And this one will also diverge based on the fact that it satisfies the conditions of the limit comparison test. So our conclusion there is to say what? Conclusion. The sum of 1 over k diverges y. Again, that is our harmonic series, or you could say P series, I guess, with P equals 1. But it's a famous series, it's the harmonic series. So since we had a positive finite number, we know both are of the same type. So the sum of 2k plus 7 over k squared plus 8k plus 3 also diverges by what test? By the limit comparison test. But only if your limit is a positive finite number. So this one, we have the sum as k goes from 1 to infinity of the square root of 4k squared plus 7 over 9k squared plus 5k plus 3. Let's make it 9k cubed. Make a small change. Let's make it 9k cubed instead. And then what I want to do is I want to recognize what my a sub k is. A sub k is the square root of 4k squared plus 7 over 9k cubed plus 5k plus 3. And I will ask you, what will b sub k be? What is b sub k? What are we going to compare it to? Preferably a sequence whose series is easy for us to determine whether or not it converges. So pick the best possible b sub k for us to compare it to. What will that be? What do we get here? Well, the top is essentially square root of k squared, right? Top is basically square root of k squared, which you could call absolute value of k. But since we're going to infinity, I'm not terribly worried about that. I can just call it k. The bottom is basically k cubed. So the square root of k squared for k being positive is just k over k cubed. And what would that become? That would become 1 over k squared. So that is the series that you should be comparing this thing to. That's the series you should be comparing this thing to. So let's go ahead and look at it. Everything is positive, so we satisfy that requirement. We're going to look at the limit as k goes to infinity of a sub k over b sub k. If I get a positive finite number, then both are of the same type. We know the sum of 1 over k squared converges because of the p series test, so I expect this will also converge if I get a positive finite limit. So this is the limit as k goes to infinity of the square root of 4k squared plus 7 over 9k cubed plus 5k plus 3 divided by 1 over k squared. So when my algebra students tell me what, keep, change, flip. So this is the limit as k goes to infinity of this first piece, square root of 4k squared plus 7 over 9k cubed plus 5k plus 3 times k squared over 1. Now, how do we handle this? How do we handle this? So the algebra gets a little tricky. Limit as k goes to infinity, square root of 4k squared plus 7 divided by 9k cubed plus 5k plus 3 times. I'm going to rewrite k squared as the square root of k to the 4th. And then what this is going to become is limit square root 4k squared plus 7 square root of k to the 4th will be square root k to the 4th times 4k squared plus 7 all over 9k cubed plus 5k plus 3. So let me ask you to go ahead and see if you can determine what that limit will be. So write down what you think that answer will be. What will the limit be? Select the best answer. And I will go ahead and prove that. And I'm not going to want to use L'Hopital here. That's just going to get messy. So I'm going to use Calculus 1 strategies. Limit as k goes to infinity of the square root. Multiplying in that k to the 4th, I get 4k to the 6th plus 7k to the 4th. Divided by 9k cubed plus 5k plus 3. All right. Now I want to divide top and bottom by the same thing. What am I going to divide the top and bottom by? The highest power. So that's k cubed. Divide the bottom by k cubed. Divide the top by k cubed. But I'm going to think of k cubed as the square root of k to the 6th. Which again, since everything is positive, I don't need to be concerned with absolute values. Where does that send me for my limit? Limit as k goes to infinity. Root 4 k to the 6th over k to the 6th plus 7k to the 4th over k to the 6th divided by 9k cubed over k cubed plus 5k over k cubed plus 3 over k cubed, which is the limit as k goes to infinity of what? K to the 6th over k to the 6th, that just leaves me square root of 4. 7k to the 4th over k to the 6th is 7 over k squared. 9k cubed over k cubed is 9. 5k over k cubed is 5 over k squared. 3 over k cubed is 3 over k cubed. Now, as k goes to infinity, what happens to this? The top goes to 7 plus a large number squared, so that's 4 plus 0. So I get the square root of 4 plus 0 on top. On the bottom, 9 plus 5 over a large number 0, 3 over a large number 0. Root 4 is 2, 9 plus 0, 0, 2 ninths. And I'm happy because that is between 0 and infinity. 0 is less than 2 ninths, is less than infinity. So the limit comparison test applies, which means both series are of the same type. So let's go back and look at our first page. What were our two series? We had this thing, the a sub k, and we had this thing, b sub k. B sub k is a sum of 1 over k squared. That converges. So what can we say? B sub k is 1 over k squared. So the sum of 1 over k squared converges by what test? By the p-series test. P-series test. All right, what was my a sub k? My a sub k was the square root of 4k squared plus 7 over 9k cubed plus 5k plus 3. So our conclusion then would be this also converges by the limit comparison test. So the conclusion is that the sum as k went from 1 to infinity of the square root of 4k squared plus 7 over 9k cubed plus 5k plus 3 converges by what test? Converges by limit comparison test. Now, if it converges, it should converge to some kind of a number. So let me ask you to jump to Wolfram Alpha or use your graphing calculator with a large N. Let's get an approximation for what that converges to. Let's get an approximation for what that converges to. So make your selection of the best possible choice amongst those listed. So here we have it. Let us take a look at our original question, which was the sum as k goes from 1 to infinity of the following. Sum upstairs, square root 4k squared plus 7 divided by 9k cubed plus 5k plus 3. I don't know, let's just do a small number here. Let's do 1 to 100 and see what we get. What does Wolfram Alpha give us if we go 1 to 100? About 0.3378. About 1 to 1,000? Does it change much? 3398. 1 to 10,000. So we're looking at various partial sums, right? 340067, okay. About 100,000. Let's take a little while longer. 340087. Can I add one extra zero? Well, I still get 340087. 340089, but I think that 34008 is a pretty good approximation, rounding it up to 0.34009. So let's stick with that one for our guess. 0.34009. So indeed, Wolfram Alpha is giving us some evidence that it appears that that thing converges to that value. We don't know what that is. That's not a nice number with a simple square root or simple fractions. Typically, it's going to be a much more complicated kind of thing. Let's take a look at one more problem. We want to look at the sum as k goes from 1 to infinity of sine of 3 over k squared. So our a sub k is sine of 3 over k squared. Typically, we want to use the limit comparison test with a p series. So what would your choice be there? What do you think? What's our best option for p sub k? Well, I'm going to use 1 over k squared. And then we're going to look at the limit as k goes to infinity of a sub k over b sub k. Which is the limit as k goes to infinity. Sine 3 over k squared divided by 1 over k squared. And let me ask you to go ahead and do that limit and choose from amongst the answers given. And I will show you how to do it. So this time I am indeed going to use L'Hopital. So I'm going to change it to the same thing as the limit as x goes to infinity, just to imply that we are dealing with real numbers as opposed to integers. Sine of 3 over x squared divided by 1 over x squared. Now to use L'Hopital, we have to convince ourselves that it's fair. Plugging in infinity, 3 over a large number, that's basically 0. Sine of 0 is basically 0, right? 1 over a large number is basically 0. So that's a 0 over 0, so L'Hopital is okay. So let's take the derivative of the top and the derivative of the bottom. So that's the limit as x goes to infinity of the derivative with respect to x of sine 3 over x squared divided by the derivative with respect to x of 1 over x squared. Let's think about this. What is that going to be? The limit as x goes to infinity of the cosine 3 over x squared times the derivative with respect to x of that, which I'm just going to rewrite it as 3x to the negative 2 to make my life a little easier. And on the bottom, what's the derivative of 1 over x squared? I'm going to write that as the derivative of x to the negative 2. So then what are we going to say? This will equal the limit as x goes to infinity of cosine 3 over x squared times the derivative of 3x to the negative 2 would be negative 6x to the negative 3. Divided by the derivative of x to the negative 2 is negative 2x to the negative 3. Okay. So where does that put us? Negative 6 over negative 2 is positive 3. X to the negative 3 over x to the negative 3 divides out. Then I have cosine of 3 over x squared. Now, what happens as x goes to infinity? So find that's 3 times the limit as x goes to infinity of cosine 3 over x squared. Well, as x gets large, 3 over a large number goes to 0. Cosine of 0, though, is what? Cosine of 0 is just 1, so we get 3 times 1, which is 3, which makes me happy because 3 is a positive finite number. 0 is less than 3 is less than infinity. So what is my conclusion? Both series are of the same type. What was my original? What did we say? We had sine 3 over k squared and 1 over k squared. The sum of 1 over k squared converges by the p-series test. Sum of 1 over k squared converges by the p-series test. So sum of sine 3 over k squared converges by limit comparison test. Let's do one more and see what you get. Let's take a look at the sum as k goes from 1 to infinity. Square root 3x plus 3k plus 7. I always make that mistake. So k goes from 1 to infinity. Of the square root of 3k plus 7 over 2k plus 5. So there's my a sub k. A sub k equals the square root of 3k plus 7. What are we going to limit compare this to? What do you think b sub k will be? So answer that question. I'm going to go ahead and look at the limit as k goes to infinity of a sub k over b sub k. What I recognize is the top is basically square root of k. The bottom is basically k, which of course is k to the 1/2 over k, or 1 over the square root of k. So the bk I'm going to use here is 1 over the square root of k. So we're going to look at the limit as k goes to infinity of a sub k over b sub k, which is the limit as k goes to infinity of root 3k plus 7 over 2k plus 5 divided by 1 over the square root of k, which is the limit as k goes to infinity of root 3k plus 7 over 2k plus 5 times what? Times root k over 1, which equals the limit as k goes to infinity of the square root of 3k squared plus 7k over 2k plus 5. Just be careful with your algebra here. We've got to divide top and bottom by the same thing if we're going to use Calc 1 strategies, or you could use L'Hopital, but I think L'Hopital is a little more challenging here on this one because we've got to mess with the chain rule. So I'll stick with Calc 1 strategies. Limit as k goes to infinity of the square root 3k squared plus 7k divided by 2k plus 5. Divide top and bottom by k, but on the top I'm going to call it the square root of k squared, which is really absolute value of x. But again, as we are approaching infinity, that's not going to be an issue. So what does this give me? Limit as k goes to infinity of square root 3k squared over k squared plus 7k over k squared divided by 2k over k squared plus 5 over k. And what will that be? What will that be? You get the limit as k goes to infinity of the square root of 3 plus 7 over k divided by what? 2 over k. I'm sorry, I divided by k, 2k over k. That's an error, right? If I divide by k, 2k over k plus 5 over k. 2k over k is just 2 plus 5 over k. Now, what will this be? As k goes to infinity, where are we? As k goes to infinity, limit as k goes to infinity, square root of 3 plus 0 over 2 plus 0, which is root 3 over 2, which again makes me happy because it's a positive finite number. 0 is less than root 3 over 2 is less than infinity. So LCT applies, which means both are of the same type. What was my original story, right? A sub k should have been this. A sub k root 3k plus 7 over 2k plus 5. B sub k is 1 over root k. And we're good there. So the sum of 1 over root k diverges by the p series, so this one does as well. Conclusion. Sum of 1 over root k diverges, which equals sum of 1 over k to the 1/2. This diverges by p series. So my conclusion, what's my conclusion? The sum of root 3k plus 7 over 2k plus 5 diverges by what? Diverges by the limit comparison test.